I have someone that you all know here. Mr. Jim Fowler and I have known each other for, what, 50 years, 40 years anyway. And in the oil business, and back in the early 1980s, Jim had a beautiful airplane. It was called a Tiger Moth. It was a World War I trainer. And actually, Jim had one that he had restored. And it was absolutely a beautiful airplane. Now, is that still living?
I've still got it.
The Tiger Moth is still alive. Yes. I remember so many times going up with Jim in the back seat of the Tiger Moth. And then I got interested in airplanes, got my pilot's license, and owned a Cessna 182 for 15 years that I flew all over the country. And it was a wonderful time. And then when I moved up here to Colorado, out of the oil business, I could no longer afford for the care and feeding of a Cessna 182. Plus, a normally aspirated engine in the mountains is not such a great idea. So I sold the airplane, and I've only flown once or twice since. I went up with an instructor here about 10 years ago, and he said, "I'll sign you off in another few hours." And I said, "Can't afford it." So anyway, let me tell you a little bit about myself. Obviously, Ashley's told you I grew up in Beaumont, Texas, and I was a baseball player. And anyway, I ended up getting a full baseball scholarship to Rice University in 1969, which is really the only way I could have gone to college, because I lived on the wrong side of the tracks. My dad worked at the refinery. At any rate, I played baseball there, majored in geology, obviously, studied under some really, really great professors there. And my senior year, I had a real tough decision, because I had offers to play pro baseball, and I had offers to go to graduate school. So I actually had a program at University of North Carolina, Chapel Hill, that I had accepted, and I went ahead and signed a pro baseball contract with the Chicago Cubs. Anyway, I had such a good year, they invited me to the big league camp, and I said, well, I can't go to the University of North Carolina. And so I wrote them and told them I wasn't going to go. And anyway, long story short, I ended up at Texas A&M while I was still playing baseball. So I made it 2 years to AAA, played all over the states, and went to big league camp a couple of times, got cut. And I just thought to myself, well, do I want to be a AAA baseball player the rest of my life? And I said, nope.
What position?
I was, well, that's an interesting, I got drafted out of high school by the New York Mets as a catcher. And my senior year at Rice, after catching 3 years, the coach came up to me and he said, hey, I got a bunch of sore-armed pitchers here, and I got a freshman catcher that I need to get ready because you're going to be out of here, so you want to get on the mound? And I said, sure, give me the ball. So the Cubs drafted me as a pitcher-catcher, and then I ended up, as soon as I signed, the pitching coach said, I want to make you a pitcher. And so anyway, that's how it all worked out. So I graduated from A&M back in the mid-70s, went to work in the oil business. That's when I met Jim. And left the oil business in 1997. I didn't particularly enjoy the oil business that much because my geology training was in field geology. I loved the field. And I didn't like sitting in an office. I didn't like slipping well logs. I didn't like the politics. Anyway, long story short, I moved up here and went to work for the Colorado Geological Survey. They needed field geologists, and so that's what I've been doing for the last 25 years. And I just retired 2 months ago. Nice. And I hate it. And the reason is I like being in the ball game. I don't want to be sitting on the bench. But I realized that this last project that I had last summer, that I had trouble keeping up with the 25-year-old, 155-pound field assistant. We had a project up near Devil's Head. Devil's Head is just south of Denver, west of Castle Rock. big area. I mean, it's 10,000, 11,000 feet. Anyway, I struggled, and I said, you know, it's time. So you know when it's time. So at any rate, I did a lot of work for the Space Foundation in the summers as well. And I did a lot of lecturing and traveling around the country. So this presentation is one of the presentations that I made for the Space Foundation back in the mid-2000s, and obviously I've modified it, okay? So let's get started. Any other, you don't need to know anything more about me. Anyway, understanding plate tectonics. Now, when I end this up, we're going to talk about the geology of this particular area. But for the most part, it is heavily dependent on understanding plate tectonics. Now, I have, what, 4 geologists in this room. So that means I can't get away with a whole lot. So, you be quiet. Okay. All right, so here's what we're going to do. We're going to go back and I'm going to give you a chronological update as to how this came about, what kind of suspicions were there based on observations, and how everything kind of came together in the mid to late 60s and how we have progressed since that time, okay? So, we want to look, the most important thing as a geologist, I've told this, I've taught field camp at the University of Oklahoma. They have a field camp right up here in Canyon City. I've taught that for 10 years. And, you know, helped them because they wanted a Colorado geologist on board. And all the kids nowadays, it's all computers, it's all cell phones, it's all the experimental apparatus that they can use. So electron microscopes, all of the different apparatus. And I said, you know what the most important instrument is to a geologist? They go, what? Right there. So you've got to be able to observe. And that's what we're going to do in putting this plate tectonic scenario all together. Okay, geological and geophysical. But the first thing that was recognized was physiographic. What is that? Well, if you look at this, you can fit all of the puzzles together. That is, the pieces, the continents fit together very nicely. Now, there's a few little problems where you kind of have to hammer things in, but for the most part, they fit together quite nicely. This was first recognized in like 1913, 1915 by a meteorologist. His name was Alfred Wegener, W-E-G-N-E-R. I think I have a picture of Alfred here. Hey, there it is. He actually was Arctic? Maybe he was an Arctic or Antarctic.
Arctic.
It's Greenland, that's correct. It was Arctic. He was an Arctic meteorologist. And as I understand it, when I was coming up through Rice, the story I heard was that Alfred somehow had an accident on one of his expeditions. He was in the hospital. And he was sitting there looking at just what we looked at, a map of all the continents, and he said, you know, I kind of moved things around, and he came up with the idea that, you know what, this is not a coincidence. So he came up with the idea of continental drift, and he got absolutely grilled. Fried, roasted, you name it, because he was a meteorologist and not a geologist or a geophysicist. He had no explanation as to the mechanisms of how you can move huge chunks of rocks, continents, around from their original positions to the positions they're in now. So, I think he passed away in, what, 1925 or so, and he was on an Arctic expedition. They may have even found him, I think. He was frozen, is that right, Dave?
Yeah, and he died at age 50 on an expedition trying to resupply one of his posts out there. Got caught in a blizzard, and he and his guide died.
Wow. And as I understand, I heard a story, and I don't know if this is true, but I understand that they did find him at some point. Yeah, okay. And anyway, okay, so he was strongly rejected. We've been around that now. Here are some of the physiographic things. We would call them topographic if they were above the ocean, but physiographic. A 65,000 kilometer oceanic mountain range exists on the ocean floor. We refer to that as the mid-oceanic ridges, okay? they're not all necessarily in the mid part of the ocean. For example, the Pacific does not have a mid-oceanic ridge. It has a ridge system that starts in the Gulf of California and then turns and goes in various directions, and we'll show that in just a second. The mid-Atlantic ridge is justifiably in the mid-Atlantic. But, as a matter of fact, Iceland sits on top of this mid-Atlantic ridge. And you know that what goes on in Iceland, especially if you're a 747 pilot, a lot of times you have to divert around Iceland because these big volcanoes start going off, okay? Now, there's also another physiographic element, and that's the deepest parts of the ocean, which were originally thought to exist down in the center part of the ocean basin, and it turns out that's totally false. Those trench systems generally are around close to the continents. We know those as the Marianas Trench and others, okay? So now, observations, these are something that, obviously need to be taken in consideration here. This just depicts where the oceanic ridge systems are. As a matter of fact, let me get where is my pointer? I thought it was here somewhere. I put it in my pocket.
I thought there was a pointer.
No, I didn't.
There's a pointer on the clicker.
Oh, it's on the clicker. Okay.
Mm-hmm.
There it is. Well, is it on the side? There it is. Okay, I got it. All right. So here we have the Atlantic Ocean. There's the mid-oceanic rift. Okay, mid-oceanic ridge, rather. And you can see, oh boy, I don't have California on there. There's the Gulf of California, there's Mexico, and this ridge comes down, splits off, heads in other directions. But for the most part, the ridge system is like the seams on a baseball. They're continuous, okay? So we just follow the ridge system all the way around, and we'll see that very similar to a baseball, you've got a continuous ridge system, okay? Now, let's look at geological observations now that we've looked at the physiographic ones. The continental crust is composed of very light elements on the periodic table. What do I mean light elements? Roughly elements 1 through 25. And the oceanic crust has a lot more of the heavier elements in it. There is a distinct difference in the mineralogical compositions of the crust of the earth versus the oceans. So we got calcium, sodium, potassium, aluminum, silicon, oxygen, which primarily composes the crust. We have those as well, but now we're looking at a lot more magnesium, iron, manganese, cobalt, nickel, etc., that are found in the oceanic mineralogical compositions. Okay, this is very important because now we got a density contrast. The density of the continents is roughly 2.7 to 2.8 grams per cubic centimeter. Okay? The density of the oceanic crust is 3.2 to 3.3 grams per cubic centimeter. That's a distinct difference. Okay? So that's something we also need to take in consideration here. I don't like the word float, but it's okay for what we're trying to do here. So essentially, you've got heavier material down below, and you've got these islands that I use a lot of times when I'm talking to kids to indicate that you've got a type of iceberg that's floating around similar to the icebergs in the ocean. The continents are now moving around, and they have to go along for the ride of whatever the crust is, or whatever the substrata in the crust, the heavier elements. That's the upper mantle. And whatever that decides however that moves, the continents have to go along for the ride. Okay? So, this was not known at the time. I was still going through the chronological stuff. Now, we knew all of this back after World War II. Okay? And we were dredging the oceans. We knew what the composition was. And we knew what the continents obviously were composed of. So, this all of a sudden started to become important because of the contrast. Okay. Whoops. There we go. Whoops. Now, make sure that we're on the right place. Okay. when we started dredging all of the, and coring the oceans, there were a lot of surprises. The main surprise was when we started drilling these cores, and that was the deep sea drilling project that started in the late 50s, was the International Geophysical Year, 1958, something like that. We had these big ships that were going out and doing cores. And what they found was confirmation that yes, these are all iron magnesium rich 3.3 density material. And when they started doing age dating, and I'm not going to get into how we know that, but radiometric dating, basically there is a ticking clock based on elements of uranium, potassium, argon, etc. that ticks off at a certain rate. And we can look at the material that is produced from that versus the original material, look at the rate and go, okay, we know when this started. We know when the clock started. So that's called radiometric dating. What we found, or what they found when they started looking at the age dates of the cores, is that when you went from the oceanic ridge and you moved outwards, the ages got progressively older and older. Wow, okay, another piece of the puzzle here, okay? So this was known back in the 1950s, okay? So, youngest near the oceanic ridge system, oldest near the continents, okay? So this is kind of what that looks like. Now, I always have trouble when I look at this slide because this is your continent. There's Alaska, North America, South America, Africa, Asia. The colors represent various ages of rock strata in the ocean. What that means is that the youngest material is very dark red. The next material that's slightly older, maybe 10, 20, 30 million years older, it's a slightly different or lighter red. And then this is even older yet. And then this is older and older until ultimately you get to the oldest material, and it is found near the trenches, which are the deepest parts of the ocean. So imagine yourself in 1960, and you're finding all of this out, and you're scratching your head and going, what the heck does all this mean? Okay? We're going to get there. There were also these things found called magnetic anomalies, which means, let me go back to this, since we're going to talk about reversals. Whoa, wrong way. Here we go. Come on, come on. There we go. Now, this represents the age. Obviously dark red, youngest, and then progressively older. Let's look at this in terms of magnetic anomalies. What the heck is a magnetic anomaly? When igneous rock, which is molten material, solidifies, the iron, magnesium, aluminum, manganese, all of those minerals have an alignment to them because we have a magnetic pole here on planet Earth. We have an electrical field here on planet Earth. So we have a North Pole and a South Pole. Everybody that's used the compass knows, okay? Hey, my needle is pointing to the north, okay? There are periods of time when we have now recognized that the Earth polarity flips. Now that's bizarre. When I tell that to kids, they go, you mean the poles of the Earth are going to flip and Antarctica is going to become Arctica? No, no, no. The interior dipole of the Earth, which is a magnet, flips. Why does it do that? Great question. We don't know. But the interior of the Earth is primarily a nickel-iron material that has a density of, what, 10 or 12 grams per cubic centimeter. It's very, very dense. We know that it is also molten from seismic work. That is continuing to circulate. So in the interior of the Earth, the core, primarily made of metallic minerals, is actually moving around. What happens if I take a magnet and I move it? I produce an electrical field. So now I have, that's why we have an electrical field here on planet Earth. Very, very important. if we didn't have it like Mars when they lost theirs because the core solidified, the solar wind is going to strip the water and the atmosphere totally away. So it's great that we've got a liquid core that is actually moving in its nickel iron material and it's creating the magnetic field because it shields us from the solar wind and the harmful radiation from the sun. Okay? So now what happens when the interior of the core all of a sudden decides that it's moved enough and now the North Pole becomes the South Pole? The rocks record that. When I solidify an igneous rock, it is going to take the magnetic characteristics of the pole so that all of the metallic elements are going to point to wherever the pole was at the time. So we can see this progression. And all of a sudden, boom, it flips. And now we go from one area in the ocean where we're coring this material and we have all the magnetic alignments pointing north, and then they come out another few hundred or few tens of kilometers, they drill another core. Now all of a sudden, you've got a polar flip. Wow, there's a lot of head scratching going on. So this was a fascinating time to be a geologist and geophysicist. Everybody is all over this, trying to figure out how are we going to put all this together. Okay? So, when we look at these magnetic reversals, here is your ridge. Whoops, doggone it. Fat hands. Oops, there we go. Okay. When we look at the ridge, so there's your mountain system in the middle of the Atlantic Ocean. We have positive polarity here and young material, young rocks, and we have the exact same thing on the other side, so it's symmetrical. And we have the same ages of the rocks here in the gray as the rocks over here in the gray. They're of the same polarity, pointing in the same direction. Then we go over here and we drill a new core in the ocean and we go, what the heck is going on? Because now this represents a polar shift and now the magnetic alignments are in the opposite direction. And the age of this is the same as the age of this, and this is flipped in the opposite direction as well. So we've got beautiful symmetry on each side of the oceanic ridges. Okay, another piece of the puzzle. Okay? There we go. Okay, let's see, I've already talked about that. Newer lava comes upward from the mantle. Here's what we found if we go to Iceland. You go to Iceland, you see that there's lots of volcanoes. That material is coming up, and there's actually something that is moving there. When that material comes up, it's forcing the older material outwards. Because I have this new material coming up, it's going to force its way into the cracks and crevices and the volcanoes. It doesn't have room to go upwards, so it moves outwards, and all of the material that was previously part of the magnetic or part of the igneous rock now is forced to move outwards. Wow. Okay, now here's what happens. Older, denser material approaches lighter. Okay, we're not going to talk about that yet. Okay. We're now going to talk about a guy at Princeton, because I think that Walt over here was at Princeton. There was a guy there named Harry Hess. Harry Hess, very brilliant oceanographer, had a great background. He was a troop transport captain on a ship back in World War II. And he got to test out these new depth finders that they have. Now this is from a story I got from one of my professors at Rice named Donald Baker, who worked under Harry Hess. When Harry was the captain of a troop transport in World War II, he was supposedly only to use the depth finder when he got close to where he was going to release the troops by dropping, by letting everybody off board or whatever. Because he had to know what was the depth of the water. So, while he was actually going in transit, he started turning the depth finder on, and he was the one that recognized in the beginning that, whoa, we got these mountains in the center of the ocean. And it's not like it's a big bathtub and it's deepest right in the center of the ocean. It becomes shallower as we get closer to the continents. It's just the opposite. Harry was evidently quite a character. At any rate, 1961 or 62, he prints a paper called Seafloor Spreading. And he recognized, because he understood how Alfred Wegener absolutely got tarred and feathered, right? Well, Harry is an oceanographer, geophysicist, so they're going to have a tough time tar and feathering him. But he prefaced the paper by saying, here's how I see this being all put together, and right now I'm referring to it as geopoetry. So that's what he called it in the beginning, was geopoetry. Okay, so here was his concept. Here's how he explained all of the pieces thus far. New material is coming up from the mantle, lower crust, upper mantle. It's moving upwards because heat rises. You've got all of this magma now that reaches the surface at the oceanic ridges, and that's exactly why you've got this volcanic activity in the oceanic ridges. That's why Iceland has the volcanoes. And it gets to the point where it can no longer go upwards, so it forces a slab of rock outwards in both directions. As the new material comes up, it then solidifies and takes on the youngest age at the time, and it also has the magnetic polarity at the time. And as this stuff comes up and moves everything outwards, if we have a polar shift, now you're going to have a symmetrical relationship on each side of the oceanic ridge, and it's also going to have the same age dates. So this is the way he explained it, and then he said, aha, when we get over to the continents, we now have 3.3 density material, the oceanic area composition, that now meets the continental plate, which is 2.7. They're not going to assimilate because they're rocks. So what happens? The denser material then has to go underneath the less dense material. The iceberg that is floating on has to then float, and the currents are now going to push the slab down, the oceanic slab, underneath the continents. Voila! We now have a depression near these areas that are now called subduction zones, and that depression is what we now know are the oceanic trenches, the deepest parts of the ocean. They're at these areas called subduction zones. Okay? So when Harry published all of this, it was actually pretty well accepted because, you know what, at least it explains a lot of things. Well, by that time, the academicians are all over this. So now you've got people all over the world that are doing research on this, and now things start to move very, very rapidly. Okay, so now we go from continental drift with Alfred Wegener in 1915. Now we've progressed to understanding the physiography and the geology and geophysics of the ocean floor, to where we've got this idea of called seafloor spreading, which was Harry Hess. Now in the 60s, we recognize that, whoa, all of these areas on the Earth crust can be broken up like eggshells, pieces of the eggshell, and they are moved around, and now we started calling it plate tectonics. So we now have segments of the Earth's crust that are bounded by certain features that are moving along separately in relation to others, and it is along those boundaries where we have a lot of problems. And now we refer to this as plate tectonics. Okay? So, we call this the unifying theory. There's still a lot of problems with plate tectonics. You can't explain everything with it, but doggone, it pulls a lot of stuff together. Okay, so I mentioned before, Pacific plate. It's the largest plate. It is bounded here. This is where, in the Gulf of California, where the oceanic ridge comes down, and comes down in through here, continues on around. All of this is part, and then the ridge gets, it heads up over this way. And now you have a trench system here. Okay, so we have a ridge, we have a trench, those are two boundaries. There's a third boundary. Can you say San Andreas Fault? The San Andreas is a strike-slip fault. A fault is a break in the Earth's crust. A strike-slip fault is where the faults move side by side. They're slipping past each other. There's a little bit of vertical movement. Now, in all the work that I've done in the Colorado Geological Survey, we have a few strike-slip faults, but for the most part, faults in geology are what we call up and down faults. So we call them normal faults or reverse faults, but they're high-angle faults. High-angle faults where one side moves up, the other side moves down in relation. Guess what? Almost every mountain range that you see out here is a result of the highest parts of the mountain being on the up-thrown block of a fault, that is a vertical fault, and the valleys are the down-thrown side. So they're very, very common here. And of course they're all covered up with debris and rubble. You can't go and put your hand on them. But the point is that the San Andreas is a third kind of boundary, and we call them transform faults for the geologists here, but we don't need to go there. They're strike-slip faults. One part is moving past the other. So now we have three major boundaries that we've discovered, and all relations in plate tectonics are a result of, they're results of movements along two of those boundaries. Now, every once in a while, we have three boundaries that all meet. We call those triple junctions. Things get really complex when you start messing with that, so we're not going there. All right, so you get the idea, okay? Now, the North American plate. Here's what's interesting about the North American plate, because that's where we live. What's interesting about it is that it's slowly moving. That is, the San Andreas is a left lateral strike slip. Is that right? Yeah. So, at any rate, San Francisco and Los Angeles will be twin cities here in about another 10 million years. So, this is this area here, the western United States, is the most complex mountain chain on the planet. It's called the Cordilleran, and that's where we are. Very, very complex. But my point is that here's our ridge system. Even though it's not identified as a ridge, it's a plate boundary. I said there were three boundaries, three types of boundaries. This is a ridge system, okay? This over here is a strike-slip fault. This over here is a strike-slip fault until it reaches here where there is a mid-oceanic ridge, or an oceanic ridge coming down through here. The strike-slip fault runs all the way up here, and we still have a ridge system sitting out here off of Washington and Oregon. Okay? So there's a lot of complexities going on here. Then we have a trench system that starts right here, and everything around here is a trench system. And that means that the oceanic material is diving underneath the continental material, which creates a lot of friction, as well as a low-lying area called a trench system, which is the deepest parts of the ocean. So now, our unifying theory here, I'm going to skip that one. Our unifying theory here now shows that if we look at crustal boundaries, okay, earthquakes. So this is an earthquake epicenter map. So let's say that we're going to take all of the earthquakes that we have recorded in the last 100 years since seismometers have been around, and we're going to use everything from a magnitude 4 or 5. We're going to plot it on a map. All of these red dots show you the locations of earthquake epicenters over the last 100 years or so, and look how well it defines the boundaries of the plates. Very little goes on the interior of the plate, except here in Hawaii where we have what's called a hot spot. The idea there is you've got this huge oceanic plate here, and you've got the mantle underneath that's trying to release heat. It does not have a ridge or a trench or a strike-slip fault, so what does it do? It has to find a way to release the heat. Boom, now we've got what we call hot spot. Same thing is happening up here at Yellowstone. It's a hot spot, okay? So it is not related to a plate boundary. But you can see here almost all plate boundaries are well defined by volcanic activity. earthquake activity, okay? So the reason is, this is where that cold, hard oceanic material that is now 200 million years old, that's where it's meeting the continent, and that's where it has to dive down underneath. Well, guess what? If I have a cold, hard slab that's absolutely diving underneath another cold, hard slab, you're going to have a lot of friction. Bingo, now you've got your earthquakes, okay? Okay, what else can I say here? We can always come back to that when we need to. Now, let's go look at the Ring of Fire. This is a slide of the volcanoes. These are all your active volcanoes. The previous one was your earthquake activity. Look at all of the volcanic activity. It is primarily in areas where you have subduction zones. Why is that? Now, let me show you why that is. If I can go back a couple of slides. There we go. Here's our convection. Well, I do have a pointer. Here's our convection. This is the material coming up from the mantle. Here's your oceanic ridge system. Think of that as Iceland. The plate is moving outwards. It's becoming older and older and colder and has a lot more water in it because of the sediments that are accumulating. It hits the continental plate right here. It has to now dive underneath, and when it dives underneath, because of the heat from the interior of the Earth, it gets remelted. What happens when it gets remelted? All this material comes up, and now we have a volcanic arc system that is on the interior of a subduction zone. And the entire Ring of Fire is just such a scenario. So wherever you have active subduction, you're probably going to have active volcanism. The Andes, another great example. Why? Because right off of the coast of South America, you've got the Nazca Plate and the Pacific Plate that are diving down underneath, or you can say that the continent is overriding them. Net result is the same, and now you get the molten material down here, and you get all this stuff rising to form volcanoes. On a side note, the kind of volcanism that you get here is different than the kind of volcanism you're going to get in Hawaii. Why is that? Because Hawaii is not part of a subduction zone. It has new material coming up from the mantle. It's very, very hot. It comes up and finds a nice place to extrude Kilauea, and then it moves outwards, and it doesn't do this dramatically. It's fairly benign. Just don't build a house in the middle of Hawaii Volcanic National Park, like some people do. At any rate, when you come to the Cascades, or the Andes, or the Aleutian Mountains, or Japan, or Indonesia and Malaysia, or the Andes, you have an active subduction zone that is bringing sediments, water, because of the accumulation of all the sediment, they're filled with water, and now you're going to take those down and you're going to heat them up. Well, it's like putting a tea kettle on a furnace or on the stove. What's going to happen? It's going to go off, and when it does go off, it's going to be very violent. That's exactly why we have the extreme volcanism that is very dangerous along these continental margins that are near subduction zones. Versus Hawaii and Yellowstone, not so much, because they don't have all of that cold, wet sediment that's being reheated as it goes into the interior of the Earth. Okay? All right. Let's see now. Have we done it all? Okay, I talked about the boundaries real quick, then we're going to be done. The boundaries. We have three kinds of boundaries, right? Told you we have a seafloor spread, that is a ridge system. That's where the stuff is coming up. We call that a divergent boundary. Why? New material is coming up. It's forcing the older material that's now solidified outwards. It's a divergent boundary. That's your ridge system. Okay, now we have a convergent boundary. This is near the continents. This is your entire Ring of Fire. This material spreads out. The Earth can't get any bigger. So therefore, I've got the icebergs floating around on the ocean currents, i.e. the seafloor, the older and I probably shouldn't say older. because the continents are much older. Point is, I've got the iron and magnesium high-density sediments and high-density material from the ocean that reaches the lighter continents, dives down underneath it. We call that a convergent boundary. This is where most of your action is, as the previous two maps pointed out, as far as earthquakes and volcanoes. Then we have our good friend, the San Andreas. So Los Angeles, San Francisco, yep, left lateral. What does that mean, left lateral? Just means that actually it's right lateral. Oops. Because the top part is moving this way, the other part's moving this way, and now I've got Los Angeles and San Francisco on opposite sides of the San Andreas. 10, 15 million years from now, they're going to be a lot closer. So the Dodgers and the Giants won't have to move so far to play each other. Anyway, this is, and then of course we reach the ridge system here. This junction is very complicated. And then you've got a ridge system that is still sitting out here. Now, real quick for you geologists, and you probably already know this, this San Andreas Fault was not here on the western part of North America 30 million years ago, 40 million years ago. There was a ridge system, which is right here. See the red? That's a mid-oceanic ridge. Well, I call it mid-oceanic. It's not, but it's a ridge system. And it is offset by another strike-slip fault here, and then the ridge system is here. And we have an active subduction zone right here. That right there is your first volcano. What is it? Mount Lassen. And then you go on up into the Cascades, you go into Vancouver, you go up through there. And now you've got active volcanism. Why? Because there's a subduction zone sitting there. Back about 30, 40 million years ago, this oceanic ridge system was out here. The entire western part of the United States had a ridge system. Where'd it go? A or an F, there's no intermediate. I gotta wake everybody up. Where'd it go? Where did the ridge system go? It got subducted. And when it got subducted, all hell broke loose. Because you're taking a mountain system and you're forcing it into a trench underneath lighter continental material. Did I say something about how the Cordillera is the most complex mountain system on the planet? There's a reason. Because it has subducted a ridge system. And it has been doing that for the last 30, 40 million years. Okay? Go ask Tanya Otwater, right? She came up with a groundbreaking paper on that. At any rate, now you get the idea of basically a little bit about how plate tectonics, whoops, okay, that's all right. How plate tectonics work. Now, why is this important? Well, obviously, for those of us in geology, well, I've already showed you how it explains locations of earthquakes, locations of volcanoes. It shows you mountain belts. I haven't talked about that much, but 30 million years ago, India was not part of the Asian continent. There was an ocean that separated India from, what? Asia. And then as that slowly started to, as India continued to move northward, it ran into Asia. And now I've got two continental masses. India, which is made of 2.7 grams per cubic centimeter. Asia, 2.7. Oceanic material in between, and the oceanic material gets subducted. And now I'm going to take two icebergs and slam them into each other. What happened? Yeah, it's called Mount Everest. It's called, yeah, Himalayas, that's right. Okay, so that takes care of our mountain belts. Now, mineral deposits, oil and gas deposits. If I'm seeing things along the eastern part of the United States, eastern part of South America, in the form of mineral, gold, silver, you name it, rare earths, anything you want, would I then want to maybe look on the opposite side, on the west coast of Africa, to see if there are similar deposits there? If the plate tectonic scenario is right, yes, that's a good place to look. And that's exactly what we've done, and obviously it has worked. Now, we have it. Every time I read a new GSA paper, Geological Society of America, about research being done, they're going back 2 billion, 3 billion years. And they're saying, we've got evidence of plate tectonics working back then. The Earth is 4.5 billion years old, okay? We only see rocks, for the most part, that are 2 billion to 2.5 billion years old here. Greenland, Australia, places like that. So we can't go back much farther than that, but right now the evidence indicates that yes, plate tectonics was active 2.5 billion years ago. Wow, pretty cool. So there's a lot of geologic history that has been subducted. Now that's another important thing. Here I'm going off on tangents. But this is really important because we look at the age of the Earth and people go, well, why don't we know everything about the history of the Earth? Several things. Number one is erosion. All of this material out here in the mountains is going to be eroded away in 20 million years, maybe 30. But the point is it's going to be gone. We'll have evidence of it because of the sediments that are going to be deposited in the low-lying areas and that are going to turn into rocks. So we'll be able to see that, but we'll never know exactly what that mountain range looked like. Okay? The other reason is that plate tectonics continues to recycle our materials. So you know what it's like? It's like going to a recorder like Ashley's doing back here and having it do a 2-hour recording, and after 2 hours it then recycles and starts over again. Well, guess what? What happened 3 hours ago, we don't know, because it's gone. Well, the Earth is doing the same thing, with the exception of a few little spots here and there where those rocks are preserved. So we get an idea of what's going on, but for the most part, it's geopoetry again when you go back 2 billion years. Okay? All right, so now, real quick, let's talk about where we are. The Sangre de Cristos. Let's see, I have to put my glasses on, but I think we're right over in here somewhere, aren't we?
Just off the map.
Yeah, there's Fort Garland. So we're right over in here. Now, this is very complex. Okay? That is, the Sangre de Cristos are a relatively new mountain range. What does that mean for a geologist? Yeah, they're 20 million years old or less. That's day before yesterday in our book. Okay? They're a relatively young mountain range. They consist of rocks that are roughly 300 to 350 million years old. They have some periods of, they have some other stuff in it, but for the most part, they're relatively young rocks. And now you have this big valley over here, and I live somewhere up in here, Westcliff. These are called the Wet Mountains. You are right at the junction here of the Sagres and the southern portion of the Wet Mountains, and it gets a little bit more complicated in here. Then the Sagres continue on down, but you've got a lot of volcanic activity in here. So now we got all kinds of stuff going on here in Huerfano County. What is this, Cuchara County? We're Huerfano? Okay. Cuchara is where? Just right down the road here? Somewhere?
In the city, the town of Qatar is just south.
Okay. But here in this area, we're looking at some complexities from the Wet Mountains, which are a very old mountain range. They consist of 1.6 to 1.4 billion year old granite metamorphic rock. And then you're looking at the volcanic activity in here with the Spanish peaks. And then you go over here to the San Juans, you're looking at more volcanic activity over here, and these are roughly 20, 25 million year old volcanic centers. And then you got this great big valley here called San Luis Valley. What the heck is going on here? Well, the geologists know we're looking at what's called the Rio Grande Rift System. The Rio Grande Rift System is a failed rift system. So imagine something 20 million years ago trying to get started in the mantle, bringing up new material similar to Iceland today, and cause a spreading center to occur. It almost did. But for some reason the mantle shut off, and we no longer have the active material coming up from the mantle to force the spreading outward. But we have elements where it started, and that is exactly what we're seeing in here. This is a part of the mantle is right here, and it's very close to the surface. How close? Yeah, 10 or 20 kilometers. That's not that far. So this is underneath mantle material that wanted to be volcanoes, and it didn't make it. But it made it enough over here to create enough heat to cause the San Juans to form because they're volcanic. And it made it up over here in a little hotspot area called the Spanish Peaks, and we've got some volcanic material out here. You've got all these beautiful dikes. A dike is magma that fills up a crack, okay? And it's of different material, so when the material outside the crack starts to erode away, the material that filled up the crack gets to stand out. Those are called dikes. You got all those around here. Those are really cool. They represent the volcanism that tried to get started and create the Rio Grande Rift to split, essentially, the central part or the western part of North America apart, but it failed. That's also why we got hot springs. You go up to all these hot springs in various locations up to the north and come back down here. Why are they there? Because down below the mantle is not so deep and it's very warm down there, so it creates enough activity to heat the water.
Jay, can I ask, you said the San Juans are like 30 million?
Yeah, I think it's somewhere 20 to 30.
Yeah.
Yeah.
But then the Sangre de Cristo Mountains that you showed there, you said there were 300 million.
No. The
wet
sun,
mountains, the wet mountains.
Oh, the wet mountains, okay.
the wet mountains.
They're like the
Yeah,
1
the
billion.
wet mountains are a very old, the wet mountains are a totally different animal. They have been up and down, moved up and down, probably 3 times in the last 1.5 billion years. There were plate margins out there that we recognize now. There were subduction zones 1.5 billion years ago. There's all kinds of cool stuff going on in the wet mountains. Then, about 600 million years ago, the wet mountains got infiltrated with a bunch of magmatic activity, which enriched it with the thorium and the rare earth deposits that I was working on here for the last 3 years. The wet mountains are 1.6 to 1.4 billion year old granite and metamorphic rock. They have been lowered to the point where they have been cooked, i.e. metamorphic rocks. Then they have been infiltrated with magma that has gone through all the fracture zones, and then they've been eroded and brought back down again and reheated, and then more magmatic activity as they rose again. They're very, very complex. Totally different animal than what we're looking at in the Sangre de Cristos, okay? And in the San Juans. So, long story short, Colorado is a fascinating place. My only regret is I don't have another 60 years to study it. I mean, I've had more fun in the last 20, 25 years with the survey, and I've been fortunate they put me on so many different projects. And the more I learn, the more fascinated I am, and the more I want to learn, and the more I want to go out there and do more field work. But Mother Nature says, yeah, well, you know, there's a termination, there's a past due date. Hopefully I'm not there yet, but the point is that I'd love to be doing this another 50 years if I could, but oh well, right? Okay, so I've gone on long enough. Hopefully you got questions? Yes, sir.
With a country in need of the rare earths, are there other places in the country where this up and down movement produces a rare earth?
Yeah, good question. Here's what happened. Obviously, the rare earths are interesting elements. It galls me, I can't believe I used the word GAL because that is gallium. But it does kind of get me mad when I see all of this stuff about rare earths and they say, oh, well, China's they're going to cut off the lithium, they're going to cut off the gallium, they're going to cut off, you know, these various other elements that are not really rare earth elements. That is, on the periodic table of elements, you will see that we have elements 1 and 2 and 3 and 4, and then when you get to like 52, they take that whole group out from 52 to 72 and they put them down below the periodic table and they call them the lanthanide series. So if those of you who are chemists understand, the lanthanide series were taken out of the periodic table of the elements, which is the Bible for chemists. They took them out because back when the periodic table was constructed, continuing to be understood, they just said, we don't have very many of these little elements, we don't know that much about them, let's get them off the main highway and put them down here in a detour zone. They called them the lanthanide series. Well, now all of a sudden, The lanthanide series are really important, and the reason is that elements 52 or 54 to 72 have distinct electromagnetic properties that we never understood until the 60s and 70s. And all of a sudden now, they're huge because of electronics, radar, all of these high-tech stuff, satellite imagery, everything. Not to mention a neodymium cobalt battery far exceeds the capabilities of a lithium-ion battery. So right now, lithium is the main thing that we use for Teslas and other types of battery storage. But it turns out that a neodymium, which is Nd on the periodic table, that's like the element 56 or 58, all of a sudden when you join that with cobalt, it becomes far better in its magnetic characteristics and electromagnetic characteristics than lithium ion. There are lots of other things in there. There's yttrium, there's europium. All of these different elements are really important now because of their electromagnetic properties. Okay, now to answer your question, where else do we find these? This is a real hot potato now because we did not do a lot of research on this, but until the 1970s and 80s, and this is where Ted Armrismacher up in did great work in the wet mountains. He was a USGS guy. Dave knows him, and did a lot of work up there. But they were primarily looking at thorium. Why? Because in the 60s and 70s, radioactive materials were considered our ticket to the future, and thorium was radioactive. And I still think thorium is very important, but it does not have the punch that uranium has. Well, they found that these rare earth elements were associated with the thorium. They went, well, okay, that's interesting. And then all of a sudden now, in the last 25 years, they've gone, holy crap, we need to understand these a lot better, and how productive will they be? So, the Trump administration, love him or hate him, doesn't matter, the Trump administration, before he left, said, we need to be less dependent on China and more independent by producing our own. So his scientists said, hey, we have 12 states in the continental US that have had previous reports of rare earth elements. And Trump says, okay, let's go to Congress and get some approval and get some money out here and find out what we can find out about this. So that's what they did. Colorado was one of the 12 states, so we had a chunk of money that was given to the USGS. The USGS said, well, we don't have the personnel. We don't know Colorado like Colorado geologists. So they called us up at the Colorado Survey and said, hey, we got some money. You got anybody that knows how to, that can do this kind of research? So that's when I got the phone call. So I was part of a USGS Colorado Geological Survey, CGS, research program over the last 3 years. What we found is that the previous reports by Armrismacher and others were very well done. They didn't focus on the rare earths, they focused on the thorium, but there was enough information there to where we could then go in and take what they had done and then go forward with that. And what we found was that all of these rare earths are not always associated with the thorium. That's the other thing. It's not a slam dunk when you find the thorium that you're going to find rare earths. But what we did find is that anywhere from 500 to 490 million years ago, there were intrusions in the wet mountains that brought up a lot of thorium and a lot of rare earths. They are found in narrow dikes. I pointed out what a dike was, right? It's a magmatic filling of a crack. Excuse me. I think I need to take a break here real quick. So, they found these dikes, Armrismacher et al., and lots of other geologists, right? Lots of academic people. They mapped all these things. And over a 500 square mile area, which covered Fremont and Custer counties, they found that the dikes were narrow on the order of 2, 3, 5 meters in width, and maybe 50 meters long at the most. And they were found all over Fremont, and Custer County. They had mapped something like 350, 400 of these dikes. So my task was to go out and resample these and map them, and if there were new ones, to find new ones. And so I was able to do that. Real quick, you know what the most difficult part of this mission was? Try getting on private property and tell them what you're doing. That's one thing I'm not going to miss by working for, being a field geologist. I mean, I'm a landowner, but you know what? I'm tired of dealing with landowners because they all want to know everything. Well, number one, so many people in Custer and Fremont County don't trust the government, me included. But the point is that they don't want people on their land. But yet, we have to get on the land to get access to map them and to also sample them. So convincing these people was very, very difficult. When I talked to Armbrustmacher, this is funny. Armbrustmacher was the guy back in the 60s that did the work up there. I said, hey Ted, how was it getting on the acreage? He goes, that was no big deal. All of Custer County and Fremont County, where we were, was owned by about 20 ranchers. So what we did was, we had a big keg of beer and a couple of cows. We had a big barbecue, told them on what we were doing, and they said, here are the keys. And we got to go and go whatever we, wherever we wanted. Those days are gone. Trying to get access now was very, very difficult. So I mapped some new dikes. I mapped the old ones. I sampled them. We got the results. The results were similar to what the previous USGS guys did. The concentrations were not that great, and there's no way you're going to be able to go and mine 200 or 300 or 400 different small deposits and make a mine out of it. So now, enter the USGS. They said, hey, we didn't give you guys all the money. We still got about $1 million. We're going to do an aeromag survey. So I'm out there on the ground, right? I'm the field guy. I'm out there with my 2 or 3, students, and we're out there sampling, doing all this stuff. Well, now all of a sudden the USGS says, hey, we're going to do an aeromag survey. It's going to be a low-level helicopter. We're going to put a great big stinger on it, and we're going to go fly low-level for about a month, do all this grid. Well, the next thing you know, the landowners are going, what? They're all, because they think, you're going to wipe our hard drives. You're spying on us. You're doing this. You're recording that, and I'm going, oh, God. And then they said, no, we're not letting you on our acreage. So now, here's what I had to do. I had to go and contact all of the groups. I went to subdivisions. I went to churches. I went to all kinds of groups. And I said, let me make a presentation to let these people know what we're doing. And that worked to some degree. So, we were still able to get access. But these are the problems that we have to deal with now, that people in the past didn't have to deal with.
All right, so what's like 100 foot off the ground, low level?
500.
500 feet.
500 feet off the ground. And that was, I've got a picture somewhere of me in the helicopter. I mean, I didn't get to go up in it because they had to have a pilot and a co-pilot, and all of the electronic apparatus was in the back seat. And they flew it out of Fremont County. So it took a month, 6 weeks to do the entire grid. And here's what they came up with. The whole purpose of the aeromag survey was to determine, is there a mother lode of magma down below the surface which was feeding all of these cracks and fissures that we may be able to get to? And it turns out, yeah, there is, but it's tens of kilometers below the surface, which means you're not going to be able to mine it. Now, we had a PhD student that was working with me at School of Mines, and what he found out was by looking at all the previous data that this is one of several plate margins that may very well go to the northwest and to the southeast, and it is in the southeast in Oklahoma. It's called the Oklahoma Allocogen. So he started putting all this together, did his PhD, he had all kinds of geochemical and geophysical work, really brilliant kid. And he put all this together and he says, okay, here's the wet mountains and blah, blah, blah. But if we go to the northwest and maybe into Utah, maybe we can find something that is a lot more extensive and easier to mine. So that's kind of the way we're going. So basically, the rare earth study that I did started out as an economic study by the Trump administration to determine the value, and it ended up being an academic study. So, and I'm done with that, and so now I'm on the bench. Yes.
And just kind of curiosity question, when you're talking like in the Cascades subduction, is it, and you know, my memory is that earthquakes on that part of the U.S. are typically offshore,
Yeah,
but the volcanoes are inshore. Is that because
yeah, the subduction
takes
zone is
more-
offshore.
So there's a distance because it takes
Right.
that time for the magma to get hot?
Yep. The subduction is offshore. The strike slip faults that are separating the ridge, they're still offshore. So that movement is offshore, primarily earthquake activity. When you get to the actual subduction zone itself, now you start to get some seismic activity, but for the most part, the volcanoes are located 50, 100 miles inland from where the subduction zone is, because the subduction zone is at an angle,
Yeah,
and you've got to heat up that rock.
right.
So by the time you start moving this stuff down and get it hot enough, then it's going to come up over here rather than where the subduction zone is. Okay?
Different part of the world. What can you say about this new continent they found subsea off of New
Yeah, I
Zealand?
read about that. And basically, here's my take on it. There were, in the Earth's history, numerous microcontinents that were moving around that ended up assimilating with the main continent. North America has not always been the size that it is now. It's been accreted. We call that accretion. There have been numerous, in the beginning when plate tectonics started, numerous small continents, islands, that have been moving around like icebergs, and they've been slammed in, and then they have been consolidated into a major continent. So we see that throughout the western United States. I mean, there's paper after paper that comes up and says, hey, found another microcontinent that 1.5 billion years ago rammed into North America, and here's my data. What happened, I think, out here with this continent that they found off of Malaysia, it's the same thing. It's a microcontinent, but you know what? I don't know. I didn't look at all the data, but I suspect that the reason it is subsea is because it was not entirely a continent, but yet not entirely oceanic material. So you've got a little bit of a hybrid there. So it's able to be underneath, and it's part of these microcontinents that back in the past moved around, and so that's why they found it. And they did geophysical surveys to do that. And I'd like to see the data, you know, but I didn't get into the paper enough.
And so Mount Blanco being on the eastern side of the San Luis Valley, from what you're saying, it's volcanic? And
That's a good question. I know the Spanish peaks are. Mount
Yeah.
Blanco, or what they call it, Blanco?
Yeah.
It's massif.
I don't, do you know, Dave?
It's an igneous massif Precambrian.
Oh, it is a Precambrian massif.
If you think of the Saga de Cristos as mainly 300 million year old Pennsylvanian detritus from the ancestral Rockies,
Yep.
all the way up and down northwest to southeast. On the eastern side, it's mostly that. And on the western side, it's for Precambrian.
Okay, yeah. All right, so what Dave is saying, this is really important. All along the Front Range, there is this material, and it's seen very easily in the Garden of the Gods. And it is of a certain age, 280 to 320 million years old, and it's this huge wedge of sedimentary debris. It's got rocks and pebbles and cobbles and boulders and sand and all kinds of stuff. And it represents the detritus meaning the erosional material, from a pre-existing mountain range that was here over 300 million years ago. We call that the ancestral Rockies. That formation of all that wedge on the east side of the Front Range is called the Fountain Formation. Very distinctive. It's all over the place. Garden of the Gods has it. I mean, I've mapped it all up and down the Front Range. And in places, it's 3,000, 4,000 feet thick. It's huge. That was a very significant mountain range here. It was deposited in some places on top of the actual mountain range that was moving up causing the erosion, which was very old material. So you have this 300 million year old stuff sitting on top of billion-year-old granite. Wow. Billion years old on the granite and 300 million years old here. Okay, where'd the 700 million years go? Yeah, great question. That's for us geologists to figure out. It got eroded away. As you come farther to the south, we can see a lot of material that was 500, 600 million years old, but it's still deposited on top of the granite. So we're still missing 300 million, 400 million years. The cool thing about geology is that we can go elsewhere and we can find the sediments that represent the stuff between the billion-year-old granite and the 600 million-year-old sediments, and then we can start putting the pieces together. That's what we do. We're just detectives. You know, we're just like CSI, except we don't have to deal with dead bodies, right? Which makes it a lot more fun, in my opinion. But at any rate, you put all the pieces together and you come up with a geological scenario, and you never know all the answers. But here along this area, and then when you get on the western side, as Dave said, now you're looking at the Precambrian rocks, which are, that's a fancy word for billion-plus-year-old rocks. And those are primarily igneous, which is granite and metamorphic rocks. We refer to that as basement rocks. So now you're looking at the basement with the sediments deposited on top of it. And then we try to piece all that together. So we look at all the different sedimentary configurations, and the changes in the sediment indicate changes in the environment that the sediment was deposited in. So we can go to the Bahamas and we can look at nice limestone and carbonate, calcium, corals. We can go to the sand dunes and we can see all these beautiful windblown sands. And we can go to the swamps of Louisiana. We can go to lakes, we can go to the oceans. We can see all of this material. Oh, thank you, dear. We can see all of these different sediments, and they all represent different environments. What does that mean? That means that if we look at all the environments today and we see the kinds of sediments that are being deposited, and we see the same rocks that came from those sediments in the geologic record, we can go, aha, this was a Bahamas platform because of all the carbonate corals, even though it's 500 million years old. Aha, we can go and see that this was oceanic material because it's the same stuff that's being deposited out in the middle of the Atlantic. We can look at the fossils. We can put all this together. And when you do that, you find out that the Earth is a dynamic place. It's constantly changing. Colorado has just 100 million years ago, actually 70 million years ago, it was totally underwater. Did you guys know that? The geologists do, but this was all underwater. This was a seaway. So, and that's not that long ago, 60 million years in the context of 4.5 billion. So it's just fascinating to me, and like I said, I hate getting old. Dave?
Well, that's a good point you made about finding things elsewhere that you couldn't find in the area you're looking at, and trying to figure out why is this missing? There's a big gap here. And Walt and I have been over on the great unconformity, they call that the great unconformity, which is the difference between the 300 million year old sedimentary rocks that are in oceans and the 1.4 billion year old basement rock, which you could call Precambrian. And Walt and I have led a field trip or two out there to show people that it's at mile marker 276 on US Highway 160. You drive out there, it's beautiful. It's beautiful vertical sediments from ancestral Rockies. And there, right next to it, is a granite that's weathered, and you can hit it with a hammer and knock out crystals. It's igneous. And so that's the space between is how many millions of years missing from 1-something billion to 300 million. That's a lot of time that all that's gone. But you can go other places around and find those rocks and then fill in, put the pieces together and reconstruct a geologic history. That's a difficult concept for a lot of non-geologists to grasp.
It is.
that you can take pieces from different parts of the world and put them all together and make a continuous
That's
system,
right.
even if stuff is missing.
Well, I mean, I have something else I'm going to talk to you about as far as the age of mountain ranges and the great unconformity. Before I do that, here's the thing that's really amazing about the way the geologic timescale was put together back in the 1800s. Geology is a relatively new science. Matter of fact, a great book, you probably read it, it's called The Map That Changed the World by Simon Winchester. There was a guy back in England who was a coal miner that really started putting geology together. His name was William Strata Smith. And this book is about him. And he was in all kinds of trouble, debt, etc. He was in prison. Anyway, he comes out of prison and he knows that he's got something as far as his understanding of strata. And it was all because of coal mines in England. Coal was huge. That was how they heated everything. So knowing where the coal was is kind of important, right? So Bill Smith, just a layman, goes out and he starts putting this all together and he starts making a map. First geologic map ever made. And it's on the wall of the museum, one of the big museums in London. It's incredible what he did. And it turns out he was pretty much right.
I'm sorry, what was the name of the book?
The Map That Changed the World.
Okay, by Bill
So,
Smith?
Simon Winchester. Simon Winchester is a geologist. That was one of his first books. He's written numerous books after that. Simon Winchester, The Map That Changed the World. The guy was named William Smith. Anyway, long story short, here's what happened. Can you say Alfred Wegener? All the scientists said, get the hell out of here. You don't know anything about that. We're the PhDs. We're the smart guys, or we're the guys that we're the professors. And by the time it was all over, in the latter part of William Smith's life, he was given the medal, the science medal or whatever, and accepted by all of the scientists because of his work. So it's a great book to read. But at any rate, here's the point. Back in the 1800s, they started putting all these fossils together, okay? Now, we're not going to get into the religion thing and all this, but basically, geoscientists put together fossils and they could see evolutionary aspects of it, and they could look at the different strata that they were deposited in, and they could say, aha, this one's younger because it's up here near the top, and this one's older because it's near the bottom. They started putting this all together. Well, because of what Dave said, here in Colorado we got a huge gap. We don't see all of these strata, but they see them elsewhere in the world. So they started putting this together. Next thing you know, the scientists started convening. They put it all together, and they put together what we now call the geologic timescale. They didn't know the ages as far as radiometric dating. That hadn't been invented. But in the 1800s, they put all this together, and now that we have the radiometric timescale and all of this advanced stuff, we put it together, and those guys nailed it in the 1800s. The paleontologists nailed it, okay? So, with that being said, Dave, here's the other interesting thing. Here, just 2 years ago, I'm out working on the wet mountains, and I'm wrapping up the project, and the survey calls, hey, we had somebody quit, and they were mapping the Royal Gorge Quadrangle. Royal Gorge, that's Canyon City. And they said, can you go out? And I was in Westcliff at the time, and I said, yeah, I can go out. So I went out January, February, and March, and I mapped the area that this person did not map because she left. And what I found had been published before, but to me it really hit home. In parts of the Royal Gorge Quadrangle, the Jurassic Morrison is sitting on the granite. Jurassic Morrison is 60, 65, maybe 70 million years old. 70 million years old, sitting on 1.2, 1.3 billion year old granite. What you just talked about was how we have an age gap of maybe 100 million years or whatever. Now what we're talking about is an age gap of what? 900 million years. That's almost 1 billion years of Earth's history. What that means is that Royal Gorge was above sea level all this time, and no deposits of new material were allowed to get on top of it because it was being eroded. And then, 70 million years ago, the youngest sediment gets deposited on top of it. I mean, this is fascinating that you've got that kind of a time gap, and that area up there was above sea level over that extensive period of time.
You can say, it's possible that things were deposited there, but they've been eroded.
That's correct.
You can't exactly
That's
know.
right.
whether
That's right.
they were-
See, what Dave is exactly right. What if between 60 million years and the billion-year-old granite, there were all kinds of stuff deposited on there, and it got eroded away, and now the only thing that's left, or that came in next, was 60, 70 million years ago, the Jurassic Morrison Formation. So these are the things that we deal with as geoscientists, and I just feel so lucky that I got to do this, you know?
It's fun.
It was fun. It is fun. And
They pay you.
I don't want to be on the bench, Dave.
They pay you for having fun.
They do, they pay, that's right, that's exactly right.
It's a fun little thing down there. There's a quarry up towards Pikes Peak from Florence. Yeah, there's a campground up there.
I know what you're talking about.
Yeah, where you go right by it going up Phantom Canyon.
Yeah.
Okay, here,
They got fossils up there.
several decades ago, I went in that office and they had a 3D microscope set up, what looked like sand on a table. You look through that microscope and instead of sand, you're looking at shells.
Yeah.
Tiny shells.
I mean, this is a whole nother game. One of the things that's, and I don't want to get in politics, but one of the big games that's going on now is all this stuff about global warming, carbon dioxide, etc. Okay, fine. We can go back and look at all of these microscopic shells that were created by calcium carbonate, calcium CaCO3, it's limestone. That's what these critters make their homes out of. These little microscopic critters make this calcium carbonate, but it has certain kinds of geochemical signatures to it that we can ascertain to determine what carbon dioxide content was at the time. And what that shows us is that you're not hearing the full story from the news media and the people that are on the bandwagon about carbon dioxide. There were numerous periods of time based on the shells that we have looked at in geologic history that show that carbon dioxide content was far greater than it is today. Well, the Earth didn't blow up. All the plants did just fine. Everything was fine. The atmosphere was fine. Obviously, the animals made it. Everything was fine. But my point is that it's not unique that we have an increase in carbon dioxide, and it does not necessarily mean that it is related to anthropogenic sources, because millions of years ago there were no people around and there was no industry. And all of this has happened in the past in Earth's history. So the more we know about the Earth, perhaps the more tame we should be about jumping on bandwagons about this crisis or that crisis or what we're doing or what they're doing, and et cetera, et cetera. Now, I'm not saying that we shouldn't pay attention to that, but I'm just saying that you don't want to get into a point where you just think that's the absolute reason that this is happening. There's a correlation between the increase in carbon dioxide and an increase in temperature of the oceans. Maybe, but correlation is not always causation. I can say, hey, the stock market's gone up for the last 100 years, and that has nothing to do with carbon dioxide. Well, maybe you could say it does. But point is that just because two graphs correlate does not mean that they're interlinked. There can be lots of other explanations. And that's the thing I've learned about being a geoscientist. You never have all the data to conclusively say this is exactly what happened. Anybody that says that, I'm going to dismiss them. because there are always alternative theories and reasons for explaining something, and it may not be your favorite hypothesis. It may not be my favorite hypothesis. So you got to look at all the data and put it all together and realize that I don't know all the answers. That could be, but I have to keep an open mind. And it bothers me when I see people that have a theory that they want to prove and they go look for only the data to support that theory and they dismiss other data. That's not good science. So, anyway, boy, did I get on a soapbox?
I enjoy it.
Yes.
I have one quick question. In this area, there's the dikes, and you've talked about them. And there's also the Dakota Wall.
Yeah.
Is the Dakota Wall related to the dikes?
No.
Is it a dike?
The Dakota sandstone, that's a good question. The Dakota sandstone is it's a mid-Cretaceous, it's, let's see, the Dakota is something like 120 million years old. It was near a coastal area, but it was probably mostly rivers and streams that deposited it. But we do have some indications that of beach properties. It has a high silica content. What does that mean? That means that when it's cemented, it's very formidable. Silica is glass. So therefore, if we cement a rock, a sedimentary rock with silica, it's going to be resistant. Okay? So the Dakota sandstone is highly silicified. It's very well cemented, both geochemically and pressure-wise. And so it forms ridges and crests all up and down the Front Range. The dikes that you're talking about look similar to that, maybe, but they are 25 million years old or younger. And they form from magma infiltrating through the cracks rather than in a beach or river type of sandstone environment.
And more likely to,
I'm sorry?
and more likely to erode.
Yeah, exactly. Yeah, now the volcanic material, the volcanic material is very fine grained. It is composed of it's what we call rhyolite. And rhyolite is very silica rich, very silica rich. Well, guess what? If I'm going to have a silica rich sediment that gets consolidated and cemented by silica, and then I have a volcanic magma that has high silica content, they're both going to be resistant, right? If I have a basalt, what does that mean, basalt? That means something like the Columbia River basalts, or even Yellowstone, or even Hawaii. Those are very iron, magnesium, manganese rich. They erode more easily because those elements do not withstand water chemically and mechanically the way silica does. So therefore I have different volcanic materials that can be some resistant, some not so resistant and more easily erodible. It's based on the chemical composition.
Okay.
Okay? Boy, this has been fun. You guys, I can't believe you sat here and listened to me.
Fascinating.
This was,
That's how we learn.
well, thank you so much for
Thank
inviting me. So now I have to drive back on 520 through mud to get to 69.
Just wait for it to freeze.
Yeah, but then I'm going to be slip sliding, so I can